Okay, last part for solar cells and photodetectors. Let's do the photodetector part, also known as photodiodes. So, if I took this simple solar cell PN junction and I hooked the leads up to an oscilloscope, you would expect that I could use the oscilloscope to see light pulses coming in. I could use this as a detector, right? And so let's talk about the specific design you use when you use it as a photodetector, which is the basis you have for anything from simple photodiodes to receivers for fiber optics to even modern digital camera devices. So what I'm going to do is I'm going to reverse bias my PN junction. That's going to help me for two reasons. One thing it's going to help me is it's going to make my depletion width a little bit larger, right? So I have a larger area to absorb carriers. But most importantly, it puts me over here in quadrant 3 where the only current I've got is my reverse saturation current, I naught. That's great because we know for a diode, I naught is really tiny, right? And so as soon as light hits this device, I can then start to see the current increase because of the optically generated current, which is in the same direction as I naught, hence being also in this quadrant as well. Now, how do you make this work a little bit better than just a standard PN junction? Well, there's two ways to do this. The first one is a PIN photodiode where I put an intrinsic region between the P and the N-type material. Intrinsic means undoped silicon. Remember, if something's lightly doped, it's going to deplete like crazy. And so, remember, the depletion region is always in the lightly doped side of a PN junction. So what I do is I take a doped region here, a doped region here, put an undoped region here, and in addition to depleting into the P-type and into the N-type material, this whole intrinsic area becomes depleted because it has no charges to uncover basically, right? And so my slope for my depletion region is spread over a larger area, but I really don't care. So if an electron hole is generated here, the electron's still going to go this way, the hole's still going to go this way. The big advantage is my depletion region has increased in width substantially, okay? What that buys me is it gives me a larger responsivity for my photodiode, which is amps per watt, which is how much current out do I get versus optical power in. And so I made this device design change to increase my photodiode responsivity, which is the primary figure of merit for a photodiode. How else could I do this? Well, one way you could do it is you could have an avalanche photodiode, which, as you might expect, is based on avalanche breakdown, but you don't go all the way to breakdown. You get close to breakdown, to the point where a photon comes in, generates an electron-hole pair, the bands are steep enough such that the electron gets enough energy that it can then relax back down to the conduction band and generate a second electron-hole pair, and so you get multiplication. So one photon could lead to multiple carriers being swept out. Looking at the design again, let's look at the PIN photodiode. For a PIN photodiode, again, I want to have a heavily doped and thin N-type layer, a metal which takes up minimum area on the top, right? I'll put a reverse bias on this, and I will then see optically generated current in this direction, and I could detect that as a voltage across this resistor here, right? And this could feed into an amplifier then. Well, if I design this correctly, what I'm going to do is pay careful attention to my absorption profile versus distance. So this is number of photons here versus distance in. So as I'm going, this is down to 0 photons, right? And so as I go further distance in, my photons are being absorbed and decreasing in number. And you can see how I designed this such that the majority of my photons being absorbed, this drop here, is in the depletion region or within a depletion region or within a diffusion length of the depletion region. And so you have to design this carefully to capture most of the light. And that's, of course, based on the absorption profiles for different wavelengths as well. Here's some spec sheets we're going to look at now. This is a spec sheet for a photodiode I could buy online at Thor Labs. Here's some of the specs. First off, notice they've got a responsivity curve here, responsivity amps per watt versus wavelength. So again, how many amps out versus watt of light in. And you can see that the responsivity peaks out and then decreases. So we'll get to that in a second. Okay. Some of the specs here, the active area is 250 microns in diameter. Okay, that's the area of the diode itself. Peak wavelength is at 750 nanometers. You get 0.47 amps per watt. That's on the spec sheet as well. The dark current at a reverse bias of 5 volts is 35 picoamps. That's your reverse saturation current. Okay, that's your reverse saturation current. And the damage threshold for this is 18 milliwatts of optical power, meaning that if you have this thing in reverse bias with 5 volts, then that will tell you, that you can't put more than this optical power on there before this thing would fry. And so what's the maximum current that would be associated with that? Well, if this is the optical power, I multiply it by the responsivity, and I will get basically, I'll call this 0.5 times 18 milliwatts, and this is in amps per watt. And so I roughly get 9 milliamps, right? And so that's the most current you could get through this thing before it was essentially would become damaged by having too much too much light. Roughly, what do you think the minimum optical power is that this thing could detect? Well, it's going to be somewhere related to the dark current here. And so the minimum power coming out is 5 volts times, 30 picoamps. So 150 or so picowatts. So your optical power is going to have to be greater than that to overcome the background amount of power coming out of the device. If you look at the responsivity, you might be wondering, why does it go up, peak, and then why does it go down? Well, that's very simple if you think about it. Okay. First off, this is based on silicon, so that we know if the wavelength of light gets larger than the band gap of silicon, then it won't be absorbed. And so this curve here, going to shorter wavelengths, higher responsivity, is just more of the photons being absorbed strongly in the depletion region. It peaks out, then it starts to go down. Why does it start to go down? Well, what happens at some point is that you get all the photons to absorb where you want, but two things kick in. One, the absorption starts to occur before the depletion region. If you go to shorter wavelengths, you're going to get more absorption before they get to the depletion region because the absorption coefficient is higher for shorter wavelengths. But also, remember, these are not converted efficiently in terms of, this is amps per watt. And so what's happening is I get the same amount of amps for the number of photons, but the watts, or the power coming in because of the higher energy photons, is increasing, but I don't get any more current. Remember, it's just going into heat, just like a solar cell. So for that reason as well, this starts to decrease. And these reasons are why we get a peak in responsivity for any given photodiode. Skip this slide if you're interested in, you use these devices, these are other terms you have to deal with for photodiodes. Here's some commercial ones as well. This is a silicon photodiode you could buy for 22 bucks. It's more of one that's used for specialty applications, so you can get much less expensive ones as well, of course. This is for high light levels. Here's the responsivity, 0.65 amps per watt. They even give you the capacitance. They give you the dark current, which is the reverse saturation current at 10 volts reverse bias. They even tell you how quickly you can have the rise time for this thing. Here's an Avalanche photodiode, more expensive. They give you the spectral response. This is the wavelengths it responds to. Here's the responsivity, 0.42 amps per watt. Well, wait a second. Avalanche photodiodes are supposed to have multiplication, right? So why would my responsivity not be higher? The previous one was 0.65 and this is 0.42. Well, you got to come down here. You have to multiply that by your gain coefficient. And so this is the responsivity without gain. If you put enough voltage on this to get it close to Avalanche, then you can multiply the current coming out by a factor of 50. So there's your amplification you get out of this device. So let's say your boss asks for an amplified photoreceiver for optical communications. He's got this signal coming in, it's really high speed and it's really weak. And so what you do is you just find a regular old fast photodiode, you hook it up to an amplifier, but you find the connecting line and capacitance and resistance just kills your max speed of detection. It's that RC time constant. And so you're saying, well, how can I get the amplifier not to be connected by a long, connection line, but could I get the amplifier to be inside the photodetector itself? Because if I could do that, I don't have to worry about charging up a line. I already have it amplified before it comes out of the device. Well, if I wanted to do that, I would use an HBT photoreceiver, which is a heterojunction bipolar transistor photoresistor. This is fast like a BJT, or like a heterojunction bipolar transistor, HBT, but it has a built-in amplifier for light, which is great. So I've got speed and amplification. So how do you think this thing works? Well, let's put 40 volts on the emitter, 0 volts out here on the collector. You know the forward bias voltage here will all appear across the reverse bias base collector. So all 40 volts appears across the reverse bias diode. And so then I'll have this thing set up. The reason why I use an HBT is I use a wider band gap material here, right? So that makes a nice little well for the electrons to be stuck so they don't diffuse over. So the electrons just sit here and do their job of letting holes zip across, right? So here comes a photon of light in, I get an electron, I get a hole, the hole goes out the back, the electron comes here, and while that electron's sitting here, before it recombines, I get a ton of holes across according to the amplification factor. So let's say my amplification factor is 1,000. How many carriers are collected if we hit it with one photon? Well, that's pretty easy. I'll have one photon come in, it's absorbed, an electron goes here. I'll get one hole out this way, right, and one electron. So I've got one to start. While that electron is here, because of the amplification factor being 1,000, I'll get 1,000 more holes across before the electron recombines. So I had the one I started with that was photogenerated, plus 1,000 more that are amplified by the BJT, so I would get 1,001 to come out the collector. And you can ask yourself, what will dominate, electron hole generation in the base or the base collector depletion region? Where is most of the photon absorption happening? Well, remember, for a BJT, I make the base really narrow. So you're not going to get a lot of absorption right here in the base, which would work, right, because an electron hole would be generated. But this is the reverse bias diode with lightly doped on either side, so the depletion region width is fairly wide. So most of the absorption occurs in the base collector depletion region. So these BJTs can be used as photodetectors. They're often called phototransistors. Here's one from Honeywell that you can purchase. But if this is a BJT, why does it only have 2 wires? Well, remember, all I need to do is put voltage across the emitter and the collector, get the base collector reverse bias as a result by putting positive voltage here and negative here. And I don't need a third terminal to go to the base, because my base terminal is provided by photogenerated electrons. So I don't need a third wire like I have in a BJT. And so if you're going to set a BJT or HBT up this way, all you need are 2 wires to set up reverse bias, and the base terminal is now basically taken care of by the photogenerated electron current here. You have to be careful now. Some people also refer to a PIN fed into a MOSFET as a phototransistor. Always check your spec sheet carefully to see what you're actually purchasing. In this spec sheet, they even say it's an NPN silicon phototransistor, so we know that it's this type of operation. Okay, that's it for photodiodes and solar cells. Some quick questions. What are the units for responsivity and what do they mean? Can I use a heavily doped P plus N diode as an avalanche photodiode? I want you to think back to the 2 types of breakdown to answer that question. And that'll tell you how you design an avalanche photodiode in terms of the doping levels. If I do a PIN photodiode, what advantage does it have over a regular PN junction photodiode? For an HBT photoreceiver, what will dominate, electron hole generation in the base or the base collector depletion region? And for an HBT photoreceiver, assume I have an amplification factor of 200. If 1 photon is absorbed in the base collector depletion region, how many carriers are collected? You should be able to answer that as well.